welcome to my video. Today I'm going to be covering a topic in higher chemistry in Unit 2, Nature's Chemistry, and it's about soaps, detergents and emulsions. Okay, so as I said, Unit 2 in the higher chemistry curriculum, the topic is soaps, detergents and emulsions. Okay, so soap first of all. Soap's been around for a really long time. Historically it was made with water, animal fats, vegetable oils and ash. And for a long time we didn't really realise what was happening here, but now we know that it's a strong base in the ash that produces the soap. And in fact, as early as 1865 we made the first liquid soap, and this made it easier to use the soap for a wider range of purposes. Now, today the process is much the same. We use edible fats and oils called triglycerides, and they undergo a process called alkaline hydrolysis. And from this we get glycerol and ionic salts. And I'm going to show this a wee bit more just to explain it a little bit better. Okay, so here on this side here, on the left side, is the triglyceride. We have the glycerol backbone here. This is glycerol, but it's formed from this backbone here. And here are our fatty acid molecules that come off here. These are long chain molecules, and these long chain bits are hydrophobic. When it reacts with sodium hydroxide, we have, as I said, the glycerol molecule, the backbone, and then we have these fatty acids combining with the sodium from the alkali to create the soap molecule here. And this is a long chain hydrophobic part here. And this is a charged head. Okay. So just to recap, soaps have the two parts to them. They have the long, it's hydrophobic, okay, tail, which likes non-polar things, and they have the ionic head, which likes polar things. And there I've done a wee representation of that soap molecule. Again, just showing you that at the hydrophilic part, it has the sodium and the charged oxygen. Okay, now the unusual structure of this soap molecule means that it can interact with hydrophobic and hydrophilic substances, and this is a really useful property. And what this does is it allows us to interact lipids, fats, oils with water, which is polar. Now if we remember what we've looked at in water before, we know it's polar because the electrons are not shared equally between the atoms, and it creates a small charge, if you like, on the atoms in the water. Fats, oils, lipids, they don't have any charge, they're hydrophobic, they don't like anything with charges on them, if you like. They like to be away from things with charge. So our soap molecule will come along. Here is a surface here with a big splodgy grease, and what happens is the hydrophobic part of the soap inserts into the fat, and here is a charged head inverted out into the polar substance, which is the water surrounding the grease. And then we have the sodium charges being dispersed in the water. And what this does is it separates, it breaks down the lipid-lipid bonds, and then you have what's called a micelle forming. I need to bring my pointer over. There we go. We have micelle forming. And this is when we have lots of these soap molecules all inverted out. The charged head is inverted out towards the polar water, and the hydrophobic part is bound to the fat here. And we have lots and lots of these forming. They break down the lipid, they separate it out, and they have lots of these balls. And we have an emulsion where there's lots of these micelles in the polar solvent, which is the water, and it disperses the lipids through the water. Now, micelles, the formation of micelles are controlled by the concentration of detergent in the actual water. Okay, so you need a critical concentration of detergent to form these micelles. If there's a lot of fat there, you need more detergent, so you need to have a lot of free detergent. It's about the free detergent there that's not bound already in micelles, because for each type of detergent you reach an equilibrium of what is free and what is bound in a micelle. So if you're having fat that you cannot remove, you just need more detergent basically to encourage the formation of these micelles. So I'm talking about soaps and detergents intermittently here, but it's because they both form these micelles. Their mode of action is very, very similar. But detergents are different to soaps, and I'll go over that a little bit now. So one of the disadvantages of soaps, first of all, before I go on to detergents, is the fact that they're not very effective with hard water. They react with the metals in hard water to form a scum, in the same way that they've reacted with the sodium and the sodium hydroxide to form the soap in the first place. Detergents are slightly different structure to soaps, and they do not react with the metals in hard water, and they can be used in hard water. So they are, as I've said, slightly different. They're made from substances like crude oil. They're long chain carboxylic acids. They have charged, well, not always charged head groups, but they do have head groups that are charged, sometimes not charged, made from ammonium sulfonate salts typically. Okay, so slightly different structure. You have different kinds, as I've said. The head groups may be anionic, they may be cationic, so these are the ionic detergents. They could also be non-ionic, and they can also be zwitterionic. So this is when they have positively and negatively charged groups on the head part of the detergent. Okay, so detergents also form micelles in exactly the same way. The other thing I would say about detergents is that anionic detergents and non-ionic detergents are the type that are typically used in our household cleaners. Okay, anionic is probably the most harsh. It will separate bonds between lipids. It will also separate bonds between lipids and proteins and denature proteins. And in fact, a commonly used anionic detergent called sodium didecyl sulfate, SDS, sometimes called sodium lauryl sulfate, is used in SDS Page. So that is polyacrylamide gel electrophoresis. So this is a separation technique used to separate proteins by size. And it can be used for many purposes actually, just to separate proteins or denature proteins. Non-ionic detergents are less harsh. They're often used in hand washes or more environmentally friendly cleaners, and we'll see that from our experiment today. So that's one of the ones I'm using. And they are often used to separate proteins from lipids in the lab when you don't want to denature proteins, because they're quite gentle, they don't denature proteins. Okay, so last thing, there's lots and lots of different types of emulsifiers we can use to distribute fats and oils through food. And I've just chosen to talk about this one here because I thought it was quite interesting. It relates back to soap. So you can create molecules based on triglycerides and glycerol. So if you remember that triglyceride is the glycerol type backbone with the fatty acids coming off. And you could react this with glycerol to create molecules that are not saturated with fatty acids, and they have some hydroxyl groups, and this allows them to be to interact with hydrophobic and hydrophilic molecules, and then what they do then is they interact with the fats, and they can distribute this with more water-based substances that are in the foods. So food oils and fats can be distributed throughout the food. Okay. The camera down to the experiment. Okay, so here I have shot glasses of olive oil. Okay, so I've got 2 for each one. So this is my hand soap I'm going to be using. This is sodium lauryl sulfate. So this is often called sodium didecyl sulfate. It is an anionic detergent. Okay, so quite a harsh anionic detergent. This is my environmentally friendly kitchen cleaner, which is non-ionic. So we said that was less harsh. Okay, so that's only 5% top. And this is fairy. So this is the harshest one of all. So if you could come up to the ingredients here, you can see that has 5 to 15% anionic surfactant and less than 5% non-ionic. So a lot of detergent in there, and a lot of harsh detergent, 5 to 15% of anionic. So we're going to see how they all behave differently. So first things first, I have my olive oil here. I'm going to use each one with hot and cold water. So first of all, I'm going to put a little bit of the hand soap in. Then I'm going to spray some of my Method. Not getting exactly the same, but you'll get the idea how it works. Then we've got the Fairy. Okay, let's put a little bit of that in. Okay. And then I'm going to put some cold water in the front ones. And some hot water in the back. And what we'll see is, in the hot water, what we'll see is the micelles form a lot quicker and a lot easier. And in the cold water, they don't form as well. So if you come down and have a look here, so this one here, this is my hand soap. Can you see here? I'll mix this. This is in the cold water. So you can see the lipid, the fat, the olive oil has been separated out into little balls. They're rising quite quickly to the top because they don't really want to be mixed in with the water at all. They're not that happy. They'd rather stay with their friends. All the hydrophobic stuff together. I mean, there is an element of density comes in there, but they're not that happy to be mixed in. Okay, so the next one is the environmentally friendly cleaner. So that is really quite a gentle detergent. And again, you can see slightly bigger micelles. Can you come in and see in the top here? Yep, so bigger globs, if you like, in that one. Here showing that not separating it quite as well as the hand wash. So the last one we're going to do is Fairy. So this is with cold water at the front and hot water at the back. I'll put them next to each other. So the bigger one's the hot water. And you can see them mixing in quite well. I mean, they still start to separate up to the surface, but it takes them a lot longer. And this is because they do have that really harsh anionic detergent there. It takes longer for them to come up. Right. Okay. Now I actually have these prepared earlier when I did a video earlier and my voice died. So here they're here. So this one is the hand wash, the Method, and the Fairy liquid. And you can see that even over time, even after a couple of hours, there is still a difference in how the fat, if you come up to the top, bring the on the top, there's still a difference in how the fat molecules are distributed. More evenly with the Fairy, less so with the Method, which has only got the non-ionic detergent, and this one here with less ionic detergent. Yep, it's less distributed than the Fairy. Okay, so that is my experiment. So that is me. I hope you enjoyed the video. Detergents and soaps, and see you next time.